Okay, now we move on to the second part. We are now on the geometric design of truck. So we're referring to the geometric design of truck to the railroad of a train. So to start with, the geometric design of a railway track includes all those parameters which determine or affect the geometry of the track. So these parameters actually that is being considered in the geometric design of a railway track includes the gradient, we have the curvature of the track, and the alignment of the track. So when we talk about gradient, we are referring to the degree of inclination. So actually that is referring to the rate of change. So the gradient in the track refers to the rate of change. It has something to do with the degree of inclination. So it has something to do with the rate of ascend or descend. So we have here the rising gradient or the falling gradient. When I talk about curvature, curvature has something to do with the horizontal and vertical curve. That is something to do with the transition curve, the sharpness of the curve in terms of radius or degree of the curve. So it has something to do, the curvature has something to do with the cant or super elevation on the curve. So the curvature of the measurement, when the measurement of the curvature of a curved track actually is expressed in radius. So actually the degree of curvature is the angle between the radii lines. So the degree of curvature is inverse of radius. So the larger the curvature, the larger the degree of the curvature, the sharper the curve is. The next one is the alignment of the track. So when you talk about alignment of the track, it has something to do with the straight line as well as the curve. So alignment of railway line actually refers to the direction and position that is given to the center line of the railway track on the ground in the horizontal and vertical plane. So horizontal alignment means the direction of the railway track in the plane, including the straight path and the curve it follows. So that has something to do with the alignment of the track system. So it is very important for our track to have a proper geometric design. To have a proper geometric design to ensure the safety and smooth running of the train is very important, and to have a maximum permissible speed carrying the heaviest axle load. So the geometric design is very important. So we have to follow the standard for proper geometric design for the safety of our train. So the necessity for proper geometric design arises because of this consideration. So these are basically the main consideration that we have to identify for us so that we have to follow the proper geometric design. So number one, to ensure the smooth and safe running of the train, to achieve maximum speed, to carry heavy axle load, to avoid accident and derailment due to defective permanent way, to ensure that the track requires least maintenance, and for good aesthetics. So it's very important, class, to have a proper geometric design. For the safety, number one, first and foremost, is for the safety and smooth running of the train. It's very important. And of course, so that the train will run smoothly and it can carry heavy axle load, and it could achieve also the maximum speed, and to avoid accident, basically for the safety purposes and to avoid accident within the trackway. Now we move on to gradient. So as we identified a while ago, that gradient are provided actually to pre-negotiate the rise or fall in the level of railway track. So it has something to do with the descent and ascend of the railway track. So a rising gradient is one in which the track rises in the direction of the movement of the traffic, and a down or falling gradient is one in which the track loses elevation in the direction of the movement of traffic. So we have to take note that a gradient is normally represented by the distance traveled for a rise or fall of 1 unit. So sometimes the gradient is indicated as percent rise or fall. For example, if the rise is 1 meter in 400 meters, so the gradient will be 1 in 400, or that is 0.25%. So we have here our illustration, our figure showing to us the rising and falling of the gradient. So we have our rising and we have our falling gradient. So that is 1 in 400 meters. So, and that is equivalent to 0.25. So we have to take note that gradients are provided to meet the following objectives. So the objective for the provision of gradient actually is to reach various stations at different elevation. Of course, stations, as the train travels on the track, on the railway track, it will encounter different elevations. So it will have different gradients. So as it travels from one station to the other station, it will travel in different elevations. The second one is to follow the natural contour of the ground to the extent possible. So as much as possible, whatever is the natural contour or topography of the ground, as much as possible, we have to follow that contour as we design our track system. To reduce the cost of earthwork. Of course, it's very costly. Our earthen materials are very costly. So as much as possible in the design of the track system, we have to limit the cost. Then we have the following types of gradients. So the following types, the gradient can either be, so there are different types of gradient. It can either be a ruling gradient, a pusher or helper gradient, a momentum gradient, or gradient in station yards. So when you talk about ruling gradient, actually, ruling gradient is being referred to be the steepest gradient that exists in a section. So which means that this ruling gradient determines the maximum load that can be held by the locomotive on that particular section. So while deciding the ruling gradient of the section is not only the severity of the gradient but also the length as well as its position with respect to the gradient on both sides that have to be taken into consideration. You have to take note that the ruling gradient is the steepest gradient. So which means steepest gradient, it rise and fall sharply. So it can be a rising or falling sharply gradient. So for this one, since that is a steepest gradient, so which means that it is nearly perpendicular in position. So we have to identify that the extra force P that is required by the locomotive to pull a train of weight W on a gradient with an angle of inclination theta. So we can have, if we're going to compute for the extra force that should be required by a locomotive to pull a train. So we have here P is equal to W sine theta, or it can be equivalent to W tangent theta, which has theta is approximately very small, or that can be equivalent to W times the gradient. Then the second type of gradient is the pusher or helper gradient. So that's one in hilly areas, also in areas wherein you're going to construct the track system, in an area wherein it is on a hilly part, so which means that the rate of rise of the terrain became very important when trying to reduce the length of the railway line. So for this one, if you are trying to construct a railway track on a hilly portion, so it sometimes need a gradient which is steeper than the ruling gradient. So that one, that gradient that is much steeper compared to the ruling gradient is what we call the pusher or helper gradient. So this one, it is provided to reduce the overall cost. So in such situation, one locomotive is not adequate to pull the entire load, so an extra locomotive is required. The third one is the momentum gradient. So the next one is the momentum gradient. So the momentum gradient is steeper than the ruling gradient and can be overcome by a train because of a momentum it gathers when running on the section. In valleys, falling gradient is sometimes followed by a rising gradient. So in such a situation, a train coming down from a falling gradient requires a good speed and momentum, which gives additional kinetic energy to train and allows it to negotiate gradients deeper than the ruling gradient. So this is very common, or this is being provided. The momentum gradient is provided for a section on a railway track in a valley, wherein you will have a gradient that is a falling gradient, then it will be followed by a rising gradient. So as a train comes down from a falling gradient, so as the train moves upward, so it needs a good speed and a momentum so it can climb the rising gradient. So we have to take note that so it needs here additional kinetic energy and need a gradient that is steeper compared to the ruling gradient. So for in the momentum gradient, in that particular section wherein there will be a momentum gradient, there should be no obstacle provided in the form of signal, so which brings the train to a critical juncture. So this is visible on a valley or a hilly area wherein there is a falling gradient then followed by a rising gradient. So it needs good speed and momentum for the train coming from a falling gradient to come up on the rising gradient. Then we have the last one, gradients in station yards. So we have to take note that the gradient in station yard are flat. So if you're going to observe the gradient on the station yard, they are flat. So because they wanted to prevent standing vehicle from rolling and moving away from the yard. So basically on the station of the train, there will be standing vehicle. The train will not be moving. So they wanted the vehicle to keep away from rolling and moving away from the yard. Then number 2, to reduce the additional resistive forces required to start a locomotive to the extent possible. So they wanted to reduce an additional force, additional resistive force that is a requirement to start up a locomotive. Then for gradient compensation curve, so we have here the curve provide extra resistance to the movement of train. So as a result, gradients are compensated to the following extent on curves. Number 1, for BG track or for broad grade, that is 0.04% per degree of the curve, or 70 over R, whichever is minimum. For MG track, that is 0.03% per degree of the curve, or 52.5 per R, whichever is minimum. And for NG track, that is 0.02% per degree of the curve, or 35 per R, whichever is minimum. R is the radius. We have to note that BG is the broad gauge, NG is the narrow gauge, and you have to take note that the gauge refers to the width of the track, and our MG is the meter grade. So for that one, if we're going to have here an illustration, find the steepest grade of 2% dig curve for a BG line with a ruling gradient of 1 in 200. So for the solution, we'll start with the ruling gradient. So that is 1 in 200. So 1 in 200, that is actually 1 divided by 200, it gives us 0.005, or that is 0.5%. Number 2, compensation for a 2% curve. This is a BG grade. So based on the BG grade, we have our that is actually equivalent to 0.04 per degree of the curve. So basically, that will be 0.04 times 2 degree curve, so it gives us 0.08%. Then therefore, the compensated gradient will be 0.05 minus 0.08, and that is 0.42%, or 1 in 238. So the steepest gradient on the curved track is actually equivalent to 1 in 238.